Welcome. So we're going to look today at time, velocity, and speed in this section of your text. So time, what is time, right? We're all in time. Time moves forward, keeps on slipping into the future, as Steve Miller Band is so apt to propose. Time is change, or rather the interval over which change occurs, right? If you freeze time, nothing can change. Everything is frozen in time. So for change to occur, especially motion, for an object to move, time has to exist. We won't get into the philosophical quandaries of time or anything like that, but just time is the interval over which change occurs. Now you can, like with position, determine specific time events and label them. Initial time, T naught. Final time, T sub f. The amount of time between two events is called the elapsed time. So when you start a stopwatch, or when the gun goes off and the Olympic sprinters race down the track, until the first person crosses the finish line and the stopwatch is stopped. That's the elapsed time between those two events, the start of the race and the end of the race. Elapsed time is similar to displacement for a position analog. Elapsed time is delta t. Delta, again, meaning change in, t meaning time. So it's the difference between the ending time, t sub f, the final time, and the starting time, t naught, or the initial time. Equation given down here, delta t is equal to t sub f minus t sub I. Again, see that the final time is first, the initial time is second. This has, of course, units of seconds, SI units, but could be hours, days, years. It just has to have units of time, but we'll be using mainly SI units. So time, though, is not a vector, unlike displacement. Displacement, the direction matters. Time is a scalar quantity. Time only has one direction, right? We go forward. So time, when you read instructions on making, soup, it's like simmer for 10 minutes. There's no direction associated with that. There's no simmer for 10 minutes north, which is different than simmering for 10 minutes south. That makes no sense. So time is a scalar quantity. With elapsed time, like with displacement, we can choose our coordinate systems. For example, if I move from here to there, I can say my initial position is 0 meters, but I can also say that the time where I start is also 0 seconds. I can choose when I start my imaginary stopwatch. So typically, when we're doing a problem, we say that the time at the start of the problem is 0. The start of the event. So the initial time, t naught, is equal to 0. But going back to the equation for elapsed time, hopefully you can see that if t naught is 0, then the equation for elapsed time becomes the elapsed time is equal to the final time minus 0. So the elapsed time is just equal to the final time. So when I stop my stopwatch, that final time is the elapsed time. They're the same quantity. Hopefully that makes sense. Rather than writing it as delta t or t final in homework problems and in the equations in our textbook, delta t or t final, which now remember are the same, is just simplified to t. T just means the elapsed time. But it only means the elapsed time if the start time is 0. So if you have a problem where there's a drag race and at the light, the cars take off and travel at some speed or some acceleration for some amount of time, you can say, well, the start time was when the light turned green. That's t equals 0. If I give you a problem where I'm sitting at a red light for 4 seconds before I start moving, well, then maybe the time isn't 0 when I start moving. Maybe the time is 0 at the start of the problem and 4 seconds later the light turns green. So it depends on the problem on how you want to set up when time equals 0 occurs. Typically it'll be at the start of the problem, but that doesn't always mean at the start of motion. So just note that t is often referred to as the elapsed time in your problems. Now, when an object is being displaced, when it's being moved from one position to another position, that occurs in some time interval. Well, that time interval can change, right? An object can move across from position 1 to position 2 over a very long time. Think of a snail crawling across the ground. Or it can move from position 1 to position 2 in a very fast time. Imagine a car driving quickly. We call that ratio, how quickly an object's displacement occurs, velocity. So velocity is the rate at which an object's displacement changes. A large velocity means that the object moves a large distance, again the magnitude of displacement, distance over time. Not distance elapsed, not distance traveled, but just distance over time. A small velocity means that not much distance has changed over time. Now, velocity has units of displacement over time. How quickly that change occurs. So in SI units, that's meters per second, or meters is often abbreviated with a small m, seconds as a small s, a lowercase s, so m over s means meters per second. So you see this a lot when talking about velocities. Now, average velocity is the rate, again, at which an object's displacement changes, measured at 2 positions. So it's the displacement over the time elapsed. If you go back to the last video, displacement is final position minus initial position. Time elapsed is final time minus initial time. But remember, we set that initial time to be 0 for most of our problems. That goes to 0, or we set that to be 0. So, final time is what remains in the denominator, and we call that just time, if you remember from earlier in this video. So average velocity is displacement over time. Note that we don't set the initial position to 0. We could, in a problem, set that to 0. For some problems that works, but not for all problems. It's much more common to set the initial time to be 0. The initial position, again, dropping something off a building, maybe you don't want the initial position to be 0. Maybe you want the initial position to be the height above the ground. So we don't automatically set that one to 0. But we do set the time 1 to 0 for most of the problems. So our average velocity with a little bar above it, this bar means average. Notice there's no little arrow on it. It is a vector, velocity is a vector, but you can't show it as a vector and an average very well. You have 2 bars, it's kind of silly. So I'm just using the nomenclature your textbook uses. So average velocity is displacement over time. Now we covered average velocity, which was displacement over time. Now, 3 more types of similar concepts, but distinct in physics. The next is instantaneous velocity. Instantaneous velocity is what you get when you take the average velocity over smaller and smaller and smaller units of time. Now this is a calculus argument, and we don't have calculus in this course. But instantaneous velocity is the velocity at a particular instant in time, and that can change as an object accelerates, and we'll talk about acceleration in the next part of this video. Next video, as the acceleration changes and the object accelerates, it changes its velocity. Average velocity is only concerned with 2 points. Instantaneous velocity is the velocity at a particular point. It is often referred to as just velocity. So when I talk about the velocity of an object, I mean the instantaneous velocity, not the average velocity. If I ask what the average velocity of an object, I'll say, what is the object's average velocity? If I want the instantaneous velocity, I'll just say velocity. Again, velocity is given by v. Technically, it is a vector. Put the little vector symbol above. Now, that's distinct from speed. There are two definitions for speed. In colloquial language, speed and velocity mean the same thing. In physics, they do not. They're related, but they don't mean the same thing. Instantaneous speed, which I just will call speed, is the magnitude of the velocity. Just like distance was the magnitude of the displacement. Distance didn't care what the direction was, it just wanted to know how far you went. Instantaneous speed doesn't care about the direction of the velocity, it just cares about the magnitude. So in your car, you have a speedometer, not a velocityometer. Ignore the phone call. So we're interested in things like speed. Once you figure out the velocity, take the absolute value of that, and you will get the speed. It is a scalar. There is no direction associated with it, and it has to be positive because it's an absolute value. Now, instantaneous speed is distinct from average speed. Average speed is just the total distance traveled. And if you remember, the distance traveled is, think of an odometer, is constantly moving in a positive direction. It's the total path length taken between 2 points. Average speed is the distance traveled divided by the elapsed time. This is distinct from average velocity. Average velocity is the displacement divided by the elapsed time. Average speed is the distance divided by the elapsed time.